I'm very happy to be able to present my project, which is on identifying macro cracks in macrocity images of concrete elements. I'm Sadegh Tale. I'm starting my third year of PhD at the College of Engineering. My dissertation is on the bio-inspired design of chemical admixtures for concrete. This is a side project that I came across during my work that I wanted to address. So we have an amazing machine called MacroCity that gives a lot of information on a vast number of samples from anthropology samples to biology and so on. And we've done a lot of collaborations with different groups. But most of the samples that we ourselves scan are cementitious porous materials. And one of the objects that we are looking for is to identify cracks. A new trend in concrete science is to try to add admixtures to concrete that, upon any damage, heals itself, which results in good durability and resiliency of concrete. So this is one of the works of one of our lab mates in the lab, where on the left he had a concrete sample with the crack. You see like the plate of the crack, and on the right he has the healed sample. But the problem he was facing, and I faced the same problem myself, is we have a lot of noise, voids, and other stuff in the concrete that can interact with the crack, and it's hard to separate between the two. Traditionally, there are a lot of ways to separate these. For example, you can do thresholding, you can do seeding and growing, and there are different type of stuff. People usually, for example, look at the aspect ratio or volume and so on. But those mostly work on samples and cracks like this, where you have a very clean background and you can easily identify. Whereas the samples that I come across are like this. This is like a simpler sample. We have other samples that have more phases. It's very hard for even me to identify where the cracks are because they're very small. They're between 20 to 50 micrometers. And it's hard to say where the crack is, where the micro voids are, and other phases are. So traditional methods that I looked at could not give me good results. They were mostly, again, like this. So this was a problem that I wanted to address. This is the overall aim of this project. It was to first be able to identify cracks and separate the phases, and then quantify these cracks, crack volumes, and assess the extent of damage in the concrete. And this can later on be very useful for field work, where you have an old building, you want to see how much damage it has taken over time. If you look at the face of the building, it might look very like good and normal, but you can take a sample, you can analyze, scan, analyze, run it through the sample, this model, and it will tell you how much repair it needs. And hopefully you won't get stuff like collapse of building and bridges that has happened in the previous years. This is a direct comparison to the image I showed you before, where here you see like the crack plate, you see the voids separated. This is done by hand. It's not easy. It takes a lot of time. So we want to automate this process and other phases that are not seen in this picture. So for this project, I've broken it into two phases. In the beginning, we thought, okay, there are a lot of images of cracks on the literature, on the internet. Let's just take them and run it and train a model with that and see if that works. So we collected around 12,000 cracks, surface cracks from the literature with, you see some diversity in them with the texture and shape of the crack and lighting and so on. And we tested different architectures with this data set. For example, with segmentation architecture, we use the most famous ones, UNet, LinkNet, FPN. And with CNN models, we use VGG, ResNet, and so on. So these there are different architectures for segmentation. The one I'm using is a kind of encoder-decoder. For example, with UNet, you take the image, you break it down to the most important object, and then you reconstruct the map. What VGG16 does here is like it extracts the information that you want. So for example, as an example, UNet with VGG16 will look like something like this. Of course, we played with a lot of different architectures. You see, and also we looked at like different CNN models, segmentation architectures, initialization, depth, and so on. These are some of the performances that we got. You can see they gave really good performances, and if you look at some of the example maps, for most models, we got like fairly accurate results. But you have to keep in mind that these are, again, surface cracks. When we use these well-performing models on our data set, and I want to emphasize that that image is like a simple data set. It only has a crack and some voids, a large number of voids because it's a porous material, but still like relatively it's two phases, pores and matrix. We got very bad performance. Some of them did not, for example, FP and VGG did not identify anything. With the other ones, they were fairly inaccurate. And this is a problem where we want to quantify these cracks. So we need fairly accurate results. That's when we decided to start the phase 2, which was build our own data set. And this is a lot of work that we've been doing for some time. It begins with casting and curing the concrete samples. We induce microcracks in them through a process of loading and unloading. We scan, reconstruct using microCT. We do human annotation, segmentation, and then we can use this data set. There are a lot of CT scan data sets in the literature, but there are very few microCT scans, especially of cracks. So this in itself will be a very valuable contribution, I believe. This is a process of microCT. These are some of the initial images that we got. I wish I had the later images here too, but you can see much more diversity and variance in them. But here you see like different levels of porousness and crack structures and so on. Right now we're at this stage, we're annotating our images, we're drawing the masks for the training. This is taking a lot of effort because we want to be as accurate as possible. But a few undergrad students are helping us to achieve this. This is the next steps we want to take. I wouldn't say it's like a domain shift, domain change, more like domain shift. We're like taking cracks, macro cracks, and transferring the learning into micro cracks. We're hoping to fine-tune the models that we train in the initial phase and then use them on our data set. And at the end of this project, what we want is to first be able to accurately identify the cracks in microphase, accurately identify the micro cracks of our porous material. We want to be able to quantify those cracks and be able to evaluate the extent of damage, but also get a map of the 3D volume of the crack. I want to thank my academic advisor, Dr. Ghahraman-Nejad, my IDSC mentor, Dr. Chapman, and also IDSC for giving me this opportunity, Dr. Siron Remas, Dr. Iskandarani, Dr. Wadapali. Thank you. And if there's a question, I'm happy to answer, or we can talk after the event. Thank you.
from the building?
Yes, that's a lot of old buildings, they do that already. For example, if you have a dam or like a bridge or so on, they take a core from the building and they analyze that. But
and is the nature of crack development such that you would expect that core to be representative of the the rest of the structure? Like you can get a good assessment? Yeah.
So usually what they do is they extract that core and they do like very, like for example, they do compressive strength on that sample to see if the compressive strength is a design compressive strength from 40, 50 years ago. But I would say like this is much more indicative of the actual state of the building rather than just doing a compressive strength test.
Okay, thank you.
Thank you.